Hello, everyone. So today I will talk about the thermodynamic modeling and experimental validation of metallurgical process using FactSage. So I'm here as a very end user of the FactSage program. So, well, a couple years ago I presented here three different cases about the vacuum oxy nitrocarburizing of tool steels, modeling and practice on calcium treatment of aluminum kiln steels with sulfur addition, and the development and additive manufacturing of oxide dispersion strengthened Inconel 718. So at that time, once you asked me how to colorize the FactSage plots, and I said I used Microsoft Paint. So, well, and I also recommended the FactSage developers to just enhance the figure module. But now I changed my mind, so you put all the plots to AI, so and just prompting, make my plots nicer, so then you get very, very good results. Okay, so, okay, again, in order to avoid boring you too much, I will keep our brief and focus on the parts related to FactSage calculations. There will be many slides, so I'll be fast. Please fasten your seatbelts. Okay, the first presentation about the production of tungsten iron boride ternary compounds by a self-propagating high-temperature synthesis. Well, why we did study is because the boride-based materials are increasingly attracting attention as they provide a nice combination of hardness, wear resistance, or just high-temperature stability. Therefore, the aim of this study is to produce these ternary borides directly from inexpensive oxide raw materials using self-propagating high-temperature synthesis, or the other name is SHS process. Well, again, before discussing the results, I would like to briefly introduce the SHS process. As you see, it is quite exothermic process and combustion-based synthesis technique once the reaction ignited, so it becomes self-sustaining. So, and it is faster and more energy efficient than compared to another furnace processing. Well, as you see on the right hand, the combustion front moves through the compacted powder and converts the oxide from top to down. Okay, so, and you get the desired alloy and slag. So, well, this slide summarizes the overall experimental workflow. First, the oxide powders were weighted, mixed, and subjected to SHS reaction. After the reaction, the metallic product was separated from the slag. And then the samples were then remelted by means of arc melting to homogenize the slag, so, and to investigate the possible temperature, high temperature phase transformation and final characterization. Okay, so, well, why we use FactSage program software for this case study? Well, to be completely honest, SHS process is not perfect, so it has some disadvantages. So, for example, when the reaction becomes too exothermic, it can be difficult to control it. So then we have to know what is going on before realizing the process. So that's why we have to use the thermochemical calculations, because there are many simultaneous reactions that has to be predicted. Well, for this reason, FactSage was used before the experiments to estimate the optimum raw materials ratios, calculate the adiabatic temperature, phase transformation, and alloy and slag composition, etc. So let's see the results. Well, one of the key parameters in SHS was the amount of aluminum. In this case, we use the aluminum as a reducing agent. So the graph on the left shows the increasing aluminum content changes the adiabatic temperature as well as the amount of alloy slag and gases. And the graph on the right shows the alloy composition evolves as the aluminum increases. Well, actually, unfortunately, the SHS process is not perfect because the gas formation occurs especially when we use the boron, silicon, and manganese oxides. So once the gas leaves the crucible, so it is not the part of the system anymore. So, and it is quite difficult to estimate the the whole process. Well, on the left, we can see that the increasing aluminum content changes the composition of gaseous products. In this case, boron-containing gases are dominant at the intermediate aluminum levels. But if we go further as an aluminum content, then as you see that the aluminum-containing gases occurs in the process. Well, on the right, you just see that the slag composition also changes continuously during the reaction, as expected when we increase the aluminum. So we reduce all the oxides and we get alumina. Well, this graph shows calculated tungsten, iron, boride, ternary diagrams. So instead of selecting the experimental compositions randomly, we use FactSage diagram to adjust the raw materials composition to obtain experimental alloys located in the different phase regions. Well, for example, in this case, XRD analysis confirmed that the SHS processes successfully produced the targeted ternary boride as well as accompanying phases. So, I mean, showing good agreement with the FactSage predictions. Well, finally, SCM and EDS analysis showed that the experimentally observed microstructures were consistent with the prediction. The hardness measurements also show that such materials are promising for the wear resistance applications. Well, this is our second case study, the aluminum X, cobalt, chromium, iron, nickel, high entropy alloys, from the cost-effective synthesis to strengthening via thermomechanical processing. Okay, why we studied this? Because this alloy system is one of the most widely studied high entropy alloy families, so that the properties can be tailored by just changing the content of the aluminum in the system. Okay, in this study we produce these alloys again directly from oxide by means of SHS process, and then just following suction casting and thermomechanical processes, we just determined the mechanical properties. Well, this slide shows, summarizes our complete processing road. So as you see that we just started with the oxide precursors and SHS, then we produce master alloy, then the master alloy just goes to vacuum arc remelting process, then suction casting, and then hot and cold rolling process just to investigate their deformability and strengthening behavior. Okay, well, why we use FactSage? Again, the same purpose, but this time, in addition to process metallurgy and alloy materials design, we also add the microstructure control as a purpose, actually. Okay, this is one of the results. So this alloy system was different compared to previous case study. Why? Because during the reduction of these oxides, gas formation was negligible. Okay, so the main losses in this case just coming from the some scattering during the high exothermic reactions. So therefore, the experimental conditions were much closer to FactSage results. Well, on the left, FactSage predicts how the stable phases change as the aluminum content increases. So, and on the right, the calculated adiabatic temperature increases significantly with the aluminum additions, and the adiabatic temperatures goes beyond the 2500 degrees Celsius, which is quite adequate to sustain the SHS process. Okay, so, well, again, using FactSage, we performed several trials with different raw materials compositions to obtain the desired final alloy. So, for example, in the graph on the left, yellow line indicates the amount of aluminum just aluminum required to introduce 0.5 moles of aluminum into accumular alloy system. Okay, so we just use this oxide plus aluminum and we get a special alloy composition. The graph on the right shows how the selected alloy composition evolves during the equilibrium cooling. And according to graph on the right, the alloy is primarily FCC at high temperatures, while secondary and tertiary phases occurs as the temperature decreases. Well, when we want a comprehensive look on the whole study area, I like the way that FactSage can do. So this phase diagram clearly shows how increasing aluminum changes the stability of multi-component alloy system. As you see that the starting point, the onset is 4-component alloy system, and now we just add aluminum. We scan the effect of the whole area, 5-component system at the different temperatures. So, for example, we can see that the alloy gradually transforms from FCC-dominated structure towards order B2 and BCC phases as the aluminum content increases. Okay, again, XRF measurements on the top, and you see the difference between as bulk composition, as obtained compositions, the experimentally, and the right is the FactSage predictions. So they are very close to the values predicted by the FactSage. And XRD patterns also follows the expected trend. For example, for alloys 0.5, alloy exhibits mainly FCC structure, while increasing aluminum gradually promotes the formation of BCC and B2 phases. Again, SEM, TEM, and EDS analysis were in good agreement with the FactSage predictions, confirming that the expected phase evolution and microstructure. Well, this is the last case study. This is purely process metallurgy. So in this work, which is still ongoing, and I'm just partly in this project, we are developing an alternative road for processing the high purity anodized titanium oxide. So we already published a paper on that, so with the previous ones. Also, we published all this case study in a manuscript, in journal. So, well, the aim is here to just develop an alternative road for producing anodized titanium oxide from ilmenite concentrate by means of a new proposed method. Here you see in the graph at the left-hand side a conventional sulfide process. So as you see that after acid digestion process, we have iron sulfide crystallization and then hydrolysis step and precipitation. But in our proposed method, we just eliminate the crystallization and hydrolysis processes, which is quite expensive and time-consuming processes. So we eliminate this. So after acid digestion, we just go to thermal decomposition process, but it is a selective one. It's supposed to be around 500 degrees Celsius. So we just keep the iron sulfide in the system. Then we just leach out this iron sulfide after calcination process. Well, okay, why we use FactSage for this case study? Of course, we use this for the Purbe diagrams, but especially we just focus on the calcination and digestion process in this case. First, we use FactSage to predict the product formed during sulfuric acid digestion, and then we use it to determine the optimum calcination temperature, predict sulfide decomposition, and identify the products before leaching process. Okay, but we encountered one problem, important limitation during this work, because neither of the FactSage PS database nor other currently available FactSage database contains compounds belonging to titanium, oxygen, sulfur, and hydrogen systems. But, well, so AIMP and AIOQ by GTT-Technologies, these databases taken from the Ab initio materials project as well as Open Quantum Materials database. So the recently introduced databases include these compounds. Well, by adding one of both databases into calculations, we just, we were able to model digestion and thermal decomposition reactions much more realistically. Well, this slide shows, for example, at the bottom here, so FactSage predictions with the experimental XRD results after acid digestion process. The calculations successfully predicted that the digestion products would mainly consist of titanium and iron sulfide compounds. Well, some experimentally observed sulfate phases appear to be a fused combination of the sulfate phases predicted by FactSage, but that's very good anyway. So after digestion, material was calcined at 400 degrees Celsius first. At this temperature, the FactSage predicted that the titanium oxysulfide would only partially decompose while iron sulfide phases remained stable. Well, we did the same calcination process at 500 degrees Celsius. So then the extensive decomposition of titanium oxysulfide and formation of titanium oxide, while all iron sulfides still remained available for the subsequent leaching process. Although 500 degrees Celsius produced mainly anatase, titanium oxide, a small amount of residual titanium oxysulfide was still remaining in the system. So therefore, the FactSage was further used to investigate the effect of several oxide addition during the calcination process, such as iron oxide, magnesium oxide, and zinc oxide. Well, this calculation showed that the available additives could promote the complete conversion of titanium oxysulfide to titanium oxide just before the leaching process. After following selective leaching and thermal analysis, FTRI and SEM analysis were done to the precipitates, and finally we saw that we obtained the titanium oxide particles between 50 to 200 nanometers particles. So just by combining of this new AIMP and AIOQ databases with the conventional FactSage calculations, we successfully designed and optimized the process while significantly reducing experimental trial and error. Okay, so these are just supplementals, mini studies. Well, the example on the left shows a basic fact flow process of pseudobrokite synthesis, including digestion and calcination steps. So we are still gaining experiments with fact flow and fact prosim. So at the right-hand side, here you see a fact prosim study on slag refractory interactions. As you see that there is a difference between equilibrium calculation and fact prosim. Here we develop an iterative equilibrium approach where the reacted slag composition becomes the input for the next calculation. So you don't have to add new fresh slag to the system, but first the fresh slag meets the refractory and it mixes, and then this mix again reacts with the refractory. So this is how you see the difference between equilib and fact prosim. Well, this is an early stage Wells furnace model that we developed with fact prosim. Of course, we are not trying to compete with kiln sumu. So at least not yet, I'm just kidding. Okay, so, but anyway, I mean, here you see at least we just prove that we can do such calculations by means of FactSage program. Okay, so I think this is the conclusion. So we use FactSage over 20 years in Istanbul Technical University. So to define especially the process metallurgy as well as for the material design. So many years. So, and it is, for us, it is invaluable tool for our experimental or modeling studies and for understanding and optimizing the existing or new studies. I also thank you very much to GTT for their valuable support. Okay, thank you so much for listening.